Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to be discussing subbasin base flow methods, specifically the linear reservoir method and the Boussinesq nonlinear method. All right, what I have on the screen here is my HMS. It's a watershed that's been delineated, and I really just need one subbasin to discuss the content of this lesson. So I'll zoom in here on subbasin 1 on the west side of the watershed and then go ahead and select that. So now that it's selected, you can see it's also selected over here in the Watershed Explorer. And then down in the Components Editor, we have the data for that subbasin that was selected and its different methods. Down here at the very bottom, we have a base flow method, and right now it's none selected. So if I go ahead and select that, we can click it and see what our options are. We're going to be talking about the linear reservoir method and nonlinear Boussinesq method. So let's go ahead and get started with that. First, we'll talk about the linear reservoir method. And this is my favorite method because it's the one only method that conserves mass. You're not relying upon the modeler to get the parameter values correct to make sure you don't have too much water. It really does take the inflow from the loss method and adds it to the inflow to the base flow. Let's click on the base flow here. This is the tab that we have to fill out all the data here for. And the first one is the number of layers. HEC HMS uses a linear reservoir base flow method to model the recession of base flow after a storm event. Water infiltrates into the soil and then back into the land into the stream network. As I mentioned, this is the only method that conserves mass within the subbasin, meaning that infiltration computed by one of the loss methods is the input to the linear reservoir. This base flow method was originally meant to be used with the soil moisture accounting loss method, but it can be used with any loss method. The first parameter here is the number of layers, and our options are 1, 2, and 3. We have to have at least one and at most 3. And as you notice, if I select a different number, it's adding a new batch of parameters for a new layer. So with 1, we see only layer 1 data. If I select 2, we have some layer 2 data. It's the same values just for the separate next layer, and then layer 3 has the most. I'm going to go ahead and just use 2 for this lesson. This is used to conceptually divide the base flow into different types of flow. For instance, type 1 may be our inner flow, and then type 2, layer 2, may be the base flow, or like groundwater that will later re-enter into the stream through exfiltration. So there's different ways to do that here. We have the flexibility to use up to 3 layers. I'm going to skip down to the GW1 fraction and GW2 fraction. This represents the partition fractions that properly allocate the amount of infiltration into each layer. So if, for instance, I said this was 0.2 for layer 1 fraction, and then layer 2 fraction was 0.5, that means 50% of the water that infiltrates via the loss method would enter into layer 2's base flow. Similarly, layer 1 would get 20% of that inflow. And then the difference between 1 and the sum of these fractions, which in this case is 30%, that would be a loss to the system entirely. And you could just assume that that goes to aquifer recharge, but it would never be water that re-enters a stream and contributes to a hydrograph at an outlet in a stream. We could also just say it's 50%, 50%, but the fact is we can't make the two add up to more than 1. It has to be at most 1 and at least 0. Next, let me go back up to initial type and then the discharge. So we have the either discharge, and if we knew what the discharge was for each layer, we could just type the value in. So say, for instance, this is 20. It's best to use this method when there is observed stream flow data at the outlet of the subbasin for determining that initial flow of the main channel. And for instance, if you don't have stream flow data, it may make more sense to select discharge per area. And now instead of the units being CFS, the units are in CFS per mile squared. So you're probably going to have a smaller number here. And then if I type in 1, for instance, and that subbasin contributing to layer 1 is, say, 20 miles squared, then we would have an initial base flow of 20 CFS. That's how that works. I'm going to go ahead and change that back to discharge. I'm going to say this is 50, and then I'm going to say this initial base flow is 80 CFS. All right. Next up is the routing coefficient. That's this GW1 coefficient in hours, also GW2 coefficient in hours for the layer 2. I'm going to assign the values of 20 hours to layer 1 and 100 hours to layer 2. These values can be estimated using measurable watershed characteristics, and the outflow from each layer is a function of the storage divided by this storage coefficient. So you can think like the smaller the number here for the storage coefficient, then the higher the outflow, the less the attenuation from the infiltration to outflow, and also the sharper and the steeper of the outflow hydrograph for this base flow. Conversely, with a larger number here for the storage coefficient, then we're going to have more of a flatter, broad-shaped outflow hydrograph for the base flow. It's going to have more attenuation, and it's going to release slower. The last field here, it's labeled as reservoirs here, but it's also mentioned as the number of steps or the number of reservoirs in the user's manual. So the number of steps, this is how to control not the decrease of attenuation, but rather the increase in lag time. So if you wanted that resulting base flow hydrograph to not only be flatter, but also experience a time delay, you would increase the number of steps here or the number of reservoirs it says. And why I think it says reservoirs is because the outflow from the first reservoir would serve as the inflow to the second reservoir, and then the outflow from the second reservoir would serve as the inflow to the third reservoir, on and on until you hit this number of reservoirs, which really serves as the maximum number of reservoirs or steps. And then ultimately, the release from that final reservoir, whatever the number is set to, would represent the release from the base flow hydrograph. The user's manual does mention that using this linear reservoir base flow method in the Subbasin tab, we have linear reservoir selected, that it was originally introduced into HMS at the same time that the loss method for this bottom selection, soil moisture accounting, was introduced. And I don't want to go into too much detail here, but lesson 23 in this playlist is where I talk about the soil moisture accounting method, and I describe 3 separate layers. There's the soil layer, and then there's sort of a top groundwater level layer, and then like a lower bottom groundwater level layer, which could all have their own infiltration. And then those 3 different infiltration layers would serve as the inflow if you're using the linear reservoir base flow method. And then 3 separate layers here, they would serve as inflow to the 3 different layers we're seeing on this screen here. But again, as mentioned, you don't have to use the water accounting method, loss method. Any loss method would work. Well, that was all I had for the discussion on the linear reservoir base flow method. The other method that I'd like to discuss in this lesson is the nonlinear Boussinesq. So if I go ahead and select that and then select on base flow, we have some similar looking parameters that we've seen in a few other of the methods for base flow, specifically the recession base flow method. But now we're assuming an unconfined groundwater layer. It's possible to parameterize the method using some measurable field data, which is what we're seeing down here. So as we've seen before, we need to specify the base flow, the initial discharge, by selecting either discharge or discharge per area. So we would type in maybe like a 1 CFS per mile squared, or 50 CFS, as if we just select discharge here. Next is the threshold type, and this works in concert with the next field down, ratio. So if we select ratio to peak, then we have to enter a ratio. If we have an actual threshold discharge value, then we would type in that number. So if I select the discharge, threshold discharge and a flow of 500, that means the base flow method would begin as soon as the receding limb of the base flow hydrograph hits 500 and below, or whatever the constant number is I type in here. However, it may be easier to scale across multiple subbasins if we use this ratio to peak, and this would be like 0.5 would represent 50% of the peak flow hydrograph on the receding limb is when that base flow method would become active. So 0.5 would be 50% of the peak, 0.1 would represent 10% of the peak, and so on. The last few fields here involve the physical characteristics of the subbasin itself. So length here in feet represents the average distance from the subbasin boundary to the stream. And this data could be determined using like GIS spatial analyst tools. The next field down is the conductivity in inches per hour. So here we're referring to the hydraulic conductivity of the average soil in the subbasin, and that would be based on field testing, but could also be approximated based on the soil type and texture and classification. Last here is the porosity, and this is the volume ratio, so it's dimensionless, of volume to voids divided by total volume. So it might be something like 42% or 0.42. And this is the drainable porosity, so that means it's the upper limit of the total porosity minus the residual porosity, because not all porosity is effective. All right. Well, that is it for this discussion on the nonlinear Boussinesq method of baseflow. And then before that, we talked about the linear reservoir baseflow method here in HEC HMS for subbasins.